Hello, statistics. Here we are, elementary statistics, chapter one in community college, and we are getting ready to learn about new information. So, one of the things we want to do is define a couple of vocabulary words right off the bat. We have data, we have statistics, we have quantitative data, and qualitative data. So, what is data? Data are numbers that have meaning, and data doesn't always have to be numbers. And this is why I gave you the definition of quantitative and qualitative right away. Those two definitions don't occur until chapter 1.2. So 1.1 is really an introduction to what we're doing in statistics, but data comes in two different forms. So data can come in the form of a number, numbers with meaning. For example, if I say seven, seven doesn't have any meaning if it's just a number. You could think of the number seven by itself. Or if I say 7 pounds, now the number has meaning. I mean, think of something that weighs 7 pounds, like a baby weighs 7 pounds. Now it has meaning. So that's data. Find the average weight of 10 babies that were born at the hospital. Well, then I can think of 7 pounds as being that average weight. That's quantitative data, numbers with meaning. Not all numbers are quantitative, though. I'll get to that later on in 1.2. The other category in statistics, numbers are always going to be quantitative or they're always going to be qualitative. Qualitative data is also called categorical data. So with categorical data, or we exhibit a quantity or a quality. So qualitative data can be non-numbers. So if I ask you, what's your favorite flavor of ice cream, or what color of car is your car? And I collect data about the percent of cars on the road that are yellow cars or red cars and so on. That's qualitative data. So we put data into two different categories. Again, data are usually numbers that have meaning. The definition in the book, they say data consists of information coming from observation, counts, measurements, or responses. So really data is just information that we use to make decisions, and that's called inference or inferential statistics. So we want to take and collect data. That's 1.3. We're going to talk about data collection. And then in chapter 2, we're going to analyze data analysis. So we want to know what's going on with the numbers. So what we do with as statisticians is take data and read it for people, or tell everyone what these numbers say. A lot of people are like, I'm not a numbers person, I don't know numbers. Well, we're going to explain what those numbers mean to the people. The second definition is statistics. Statistics, science of collecting, organizing, analyzing, and interpreting data to make decisions. A lot of people ask me, what is statistics? I've been teaching statistics for many years now, and a simple definition of statistics is that statistics is more like a science class and not a math class. There are mathematical calculations, which makes it mathematics. For example, Cal Poly San Luis Obispo has statistics as their own department. It's got its own meaning, and I think that statistics as a science class means that we're going to make hypothesis, we're going to make conclusions, we're going to have to do a lot of reading. When in doubt, read the book. If you don't know what's going on, the book has all the answers, and not just your notes or what you see on a quiz or a test. So Google, really helpful with a lot of stuff, but Google can be misleading. YouTube doesn't always have what you're trying to find, although you're probably watching this on YouTube right now, and hopefully I'm giving you some guidance to what statistics is. So a better definition of statistics comes from a sample. So I'm going to represent a diagram here, and you'll see these diagrams throughout our elementary statistics books. In fact, there's one on page 3. So if you go to page 3, you'll see a big rectangle, responsive all employees. This rectangle represents a population. So populations, sometimes they're called target populations. Within a population, we're going to take a sample. So this circle represents a sample. So if I say my population is all college students, I'm only talking about students in college. I wouldn't survey children or people not in college, elderly. So my population, if my population is all college students, and I want to know what's going on with all college students as my population, I'm going to take a sample of college students. And how do you take that sample? Typically, you're going to ask a question, and that question comes via a survey. So if I ask my population of all college students, what's your GPA? I'm not going to ask every single college student in the United States, what's your GPA? So I'm going to need to take a sample of those students. Maybe I ask 100 students across the United States, what's your GPA? And come up with an average GPA. From the sample, I get a statistic. So there's the title of the class, statistics. Say that 5 times fast. I know when you start taking statistics, a lot of people struggle with saying the word. I know I did when I first started out understanding statistics. Within a sample, we're going to get a mean or a proportion. If your data comes as a mean, that's usually quantitative data. Some data that's quantitative, there's exceptions to every rule, but most data that comes as quantitative, we can find the mean. Qualitative data, typically we're going to find 8%. Qualitative data is you're asking yes, no questions. So we're going to take a sample. From that sample, we get a statistic. For example, I want to know what your blood type is. I want to know what the percentage of people in the US are type O blood. So I'm going to take a sample of your blood. It doesn't make sense for me to drain all of your blood to get your blood type. That would be a population, taking your blood. So I'm going to take a sample, and from that sample, I'm going to find a statistic. And that statistic is the title of this book and the title of this course. We're going to take data, and from that data, get a statistic and make inferences about the population. So if our statistic comes in the form of a mean, we use this symbol X bar to be a sample mean. That gives us the population parameter. Let me write this out real quick. I know I use my mouse. I know there's better methods to write. It's just what I'm accustomed to. Some people use different apps and things like that with a writing pen. I don't have that much writing here. So I got a parameter, which is measured as usually mu. Mu represents the population mean. That's mu, mu. The parameter represents a population. So if I'm talking about all or everyone, I'm talking about a population parameter. So these are a giveaway for if you're talking about a population parameter, all or everyone in a certain population. If you're talking about a sample, you'll be given a sample value, 100 college students. Okay, the sample is the 100 college students. 100 college students were surveyed, and 40% of them have taken statistics. Okay, that 40% is the statistic. The sample is the 100 people that I surveyed. From the sample, the goal is to make inferences about a population again. If I use a parameter and make conclusions about a statistic, well, I can't really do that. Okay, it's not a vice versa type of thing. A parameter would be something like the average male is 5 feet 9 inches tall. Okay, 69 inches tall. That is a parameter, a population mean. That tells me something about all or everyone. So there's alliteration there, population, parameter. We got the P's. We got sample, statistics. We got the S's. Statistics go with samples. Parameters go with populations. So one of the things you're going to have to be able to do here is identify between a parameter and a statistic. This is example 2, page 4 of the 8th edition of the Larson Elementary Statistics book. In the United States, a survey of about 9,400 individuals aged 15 and over found that such individuals spent an average of 5.19 hours per day engaged in leisure and sports activities. Wow, 5 hours per day. That's a lot of time in sports activities. That matters, but the idea is, does this describe a population parameter or a sample statistic? Well, they said they surveyed 9,400 people. Survey. From the survey, we got a sample of 9,400. The statistic is the 5.19 hours. The statistic is not the sample. They go together. They work together. Okay, sample statistic. The freshman class at a large university has an average SAT math score of 514. There was nothing about a survey. Well, I understand that this data has to come from a survey somehow. How did he get the information? But we would get this information and find a parameter. It doesn't say anything about a sample. So we assume you're talking all students at that university or every student at the university. Therefore, that would be the entire freshman class. You're talking about a population parameter. So the first one was a statistic, the second one's a parameter. Cool. All right. A couple more definitions here in 1.1 before we complete this section. As introduction, there's 2 types of fields of statistics. There's descriptive statistics and there's inferential statistics. In descriptive statistics, you're really just collecting data and summarizing data, displaying data. So these are things like making graphs, pie charts. We're going to learn all about this in chapter 2. Bar graphs. You could do a histogram, a dot plot. Most common, though, are bar graphs and pie charts. Pie charts, I know in our college, they publish a newspaper, and every month in the newspaper, there's a pie chart talking about the budget. What % of the budget is spent on certain items? Okay, so statisticians will take data and transform it into a pie chart. So that's descriptive statistics. Inferential statistics, trying to make a conclusion about a population. So you take and collect data, find some probabilities or find a mean, and then from that value, if it's a large enough sample, if your sample's independent, if your sample is random, then you can make conclusions about the population. So that would be an inferential statistic, okay, or a study of inferential statistics. So again, we got to determine whether a data set is a population or a sample, and then we have to be able to identify the population and the sample, and then we have to distinguish between a parameter and a statistic. So that's 1.1 in a nutshell. Hopefully you know a little bit more about statistics. Okay, now that you did chapter 1, section 1, we're on to 1.2. Trying to learn about classifying data. I already mentioned classifying data as quantitative or qualitative. So there's a couple ways to collect that data and put it into different groups. Those are called the levels of measurement. So we're going to go through all of those things and try to distinguish between quantitative variable and a qualitative variable. So let's go to types of data. As mentioned, quantitative data and qualitative data. Quantity is an amount. So there are data that can be represented as numbers. Not all numbers are quantitative data. So we have data that's quantitative. We're going to say things like usually a mean. If we can find the mean of our data set, then we're talking about quantitative data. Also, numbers that have meaning, like I mentioned, anything that has to do with the human element, like average weight, average height, cholesterol, blood pressure, those are all numbers with meaning. So typically numbers oriented. Put that up there. Qualitative data, as mentioned as well, this is when you're talking about percents. And those are often non-numbers. And sometimes we use the word category or categorical data. That's another word that you'll see. That's qualitative data. And in the word qualitative, you see the word quality, as mentioned, and quantity. Some data that are numbers are not quantitative. So let me give you a few examples of numbers that are not quantitative, but are numbers. So we have social security number. You can't really find the mean of your social security number. I could, but that doesn't, the social security number doesn't have meaning to us. Another number that doesn't have meaning would be like your address, phone number, student ID number. Like I said, if those numbers are all qualitative because they're just telling me something about you, that's data that I collect about people. Okay, so if I'm going to do a survey and I work for Gallup poll, the National Institute of Statistics, the Bureau of Labor Statistics, these are all the Associated Press. These are all companies that collect data about people. They would collect your address, phone number, and other things that have to do with you in case they need to contact you for anything. And that information obviously it would be confidential, but it would be qualitative data, even though they're numbers. Within the data types, there is 4 levels of measurements. So we have, and they're kind of in order. We have nominal data, or I'm sorry, nominal level of measurement, ordinal level of measurement, and interval level of measurement. Interval and ratio are very similar. I'll distinguish the difference between those two here in a minute, but nominal level of measurement, that just means you're going to name something. So if you name anything, nominal means name. You're just naming the color of your car, your favorite flavor of ice cream. I mentioned those already. Color of car. Blood type would be one. Blood type. Ice cream flavor. These are common ones. I mean, you're going to see them in the textbook. You can refer to them out of the book when you get there, but those are all nominal levels of measurement. There we go. I've been trying to do that. Ordinal level of measurement, that means you're going to have some kind of order. You're going to order things. Sometimes ordinal can be qualitative or quantitative. I'll show that in a sec. But if you're ordering things in terms of number, we're going to have some kind of rating. Okay. So a common one would be like movie ratings. Like if a movie's rated G, PG, PG-13, rated R, etc. That would be ordinal level of measurement. Interval level of measurement, self-explanatory. If you're measuring at the interval level of measurement, then you're talking about numbers. Anything that happens over time usually is considered the interval level of measurement. You're going by units. Okay. Age is interval level of measurement. If I'm doing a survey and I want to measure something about your age, like what is your favorite pizza topping, and I would put people in age groups, 10 to 20 years old, 21 to 30 years old, 32 to 40 years old. I would use interval level of measurements. As mentioned, interval and ratio are very, very similar. Ratio level of measurement, if you're going to be at the ratio level of measurement, you're going to compare two things. So usually with ratio, we're going to do something like a fraction. Or if we do like a 2-to-1 ratio, one is twice as big as the other. Okay, so if I'm at the ratio level of measurement, I'm going to measure the amount of rainfall between two different counties. Okay, so Mono County, where Mammoth, Eastern Sierras is, and Santa Barbara County, Mono County gets twice as much rainfall as Santa Barbara County in the month of November. So if I'm measuring rainfall, I could use a fraction. A ratio level of measurement is going to give me a ratio between the two areas. So very, very similar. Both are quantitative data. So if I was going to measure it, nominal level of measurement is always qualitative. So I'm just going to abbreviate here. Nominal level of measurement is always qualitative. Ordinal level of measurement could be either qualitative or quantitative. So oftentimes when you're given a problem, when you're working in statistics, you got a statistics brain on, you're going to decide what's your level of measurement first. Or I'm sorry, what's your type of classification first, and then what's your level of measurement. Although the book doesn't really do that. They just ask you, decide what type of your data you have, and then there's different problems that say give the level of measurement. I encourage you to do both of these things. Find the level of measure, or find the type of data first, and then find the level of measurement. So interval and ratio both are quantitative data. You're measuring a quantity. Here's the big difference. So I'm going to refer to a page here. If you go into the book to decide what the difference is between interval and ratio level of measurement, in the 8th edition, if you're using the 6th edition, that is a little bit old. I'm not sure if it's going to be on page 12, but in the 8th edition, we're on page number 11. So we go to page 11. There's a paragraph after the definitions of interval and ratio levels of measurement. So this paragraph, it says, an inherent zero is a zero that implies none. For instance, the amount of money you have in a savings account could be $0. So again, this is called inherent zero. This is a great paragraph describing the difference between the two levels of measurement. Inherent zero measures none. So it's measurement. If you have $0, that's an amount of money that you have. You have $0 in your bank account. And then they go on to talk about 0 degrees Celsius. If you're at 0 degrees Celsius, that doesn't mean there's no temperature. That just means there's 0 degrees. Okay. So Celsius scale would be considered interval level of measurement. The amount of heat in the air, and dollars in your bank account would be ratio level of measurement. You could have one person can have $5,000 in their bank account, another person can have $1,000 in their bank account. That's 5 times the difference. Therefore, that's a fraction. 5 to 1 is the ratio level of measurement. You could also do some search in Google and learn more about inherent zero, but that is pretty much everything you need to know about the levels of measurement. Page 12. Page 12 is a great place to bookmark. I refer to bookmarking your textbook pretty often. If you get the little tabs or get a piece of paper, put a bookmark here when you're working on chapter 1 and 2 quiz and test. Page 12 is very useful in getting some examples of levels of measurement. Nice little table there, summary of the 4 levels of measurement. And it'll help you distinguish between interval and ratio. Their examples are the amount of or temperatures could be interval, and then amount of rainfall could be ratio. Hope you learned about levels of measurement and types of data. Go ahead and practice 1.2. Check the homework. It's in Canvas. And good luck. All right. We're on the 1.3 already. Hopefully everything is moving on along well for you, and you're doing all your work, staying up with the course. 1.3 is about data collection and experimental design. There's going to be a lot of information. This is where we start using our calculator a little bit. So if we have your calculator by now and your textbook, obviously, to learn more about what we're doing with statistics. So let me open up this page. 1.3 data collection. So within data collection, there are 3 major topics that come forth here. I kind of wish that the book had a section on each of these things. So within data collection, there is statistical design. So if we data collection, if we collect data, we're going to go out and ask people questions. Okay, we want information. I don't know if it ever happened to you, but you're over at Walmart shopping for groceries and someone's standing in front of the Walmart and asking questions. They got a clipboard and you're like, I'm too busy. I got to go to the store and buy my stuff. And then you wander around for a half hour looking for groceries. People are always looking for data, and it's a job. It's a job in statistics, and I actually had a job in statistics. That's how I got my start in statistics 20 years ago. So collecting data is really difficult, especially when people don't want to participate. You get that random phone call on your phone. It's not always a limited warranty on your car. Okay. So you can always participate in these types of data collection things from different companies. They're going to call and they're going to ask for information. In fact, they'll pay you. There's a lot of places online where you can participate in surveys and experiments, and people will pay you to participate in their study. So a survey, I just mentioned a survey, people are going to ask you questions. I participated in the Reader's Digest survey. They wanted to know how much TV I was watching. And I wasn't a very good participant because I don't watch very much TV, and it was all about binge watching and Netflix shows and stuff like that. So I'm not a very avid TV or movie watcher. I have 4 children, so I spend a lot of my time with them, along with teaching and my other extracurricular activities that I like to participate in. So statistical design, again, you're going to do a survey. You're just going to ask questions. We don't really have an opportunity to go out and do surveys in a regular semester or a regular course. I would do a final project, and that project consists of going out and asking people questions and getting their data and making some kind of inferential statistics conclusion about the data. Another method of collecting data, it's called an observational study. You're going to observe something happening, say in your community, or something going on with data that's already been collected. Observational study, usually the data has already been collected, and we look at the data after the fact and say, what's going on with this data? So an experiment hasn't been done. We're not asking people questions, so the data is already there. An example of this would be what percent of cars stop at a stop sign? What percent of vans stop at a stop sign? What percent of construction workers stop at a stop sign? Two-way, three-way, and four-way stops. Well, that'd be a nice project to come up with what percent of people actually stop. I've had students do this in the past, and they usually go sit at random stop signs around the city, and they would find what percent of people stop signs. It was an interesting topic. For an observational study, you're observing what would happen. Simulation, there's simulators. If you want to become an airline pilot or drive a train, or you want to decide what the braking distance is for a car or how safe a car is, you're going to create a simulation. So the simulation is safe for everybody involved. I'm not going to ask people to go out and drive their BMW, 60 miles per hour and crash it into a wall and see if you survive. That's unethical. Obviously, it's not going to happen. So we use driving simulators to decide which cars are the safest on the road. Plane flight simulators. When I was a student, I learned how to drive a car using a driving simulator. Different things can be done. I saw simulations where they took, it was an experiment actually, but they simulated driving on a road course, and they put people into two different groups. One group drank alcohol and they had them drive on the road course. Another group, they sleep deprived them, like 24 hours, no sleep, and they had them drive. And both did really terrible, but the people that lacked sleep actually did worse. I'm not encouraging drinking and driving or anything like that, but I'm discouraging being sleepy and driving. That is dreadfully worse than driving when you're intoxicated. That's why a law was passed a few years back. 16 hours without rest is the max that you can drive without sleep. So that's a simulation, examples of simulation. The last one, experiment. There's a lot of properties of experimental design, so I'm going to go in depth about experimental design, probably a little bit more than what's in the textbook. So hopefully when we get to experimental design in a little bit, I'll be able to give you some more information about experiments. But collecting data, sometimes when you collect data, you need to decide first, how are you going to collect the data? And then in my information, if I'm doing an experiment, survey, or observational study, the sampling technique used, so I put this up here second, sampling techniques. Are we going to do a census? Are we going to ask everybody in the population? I talked about population samples. Every 10 years, the United States government attempts to do a census where they're going to ask everybody a question about their household income, ethnicity, and things like that. So that's a census. You're going to ask everybody in a population. So if I do a census of students at Hancock College, I would probably want to know what percent of students actually drive to school or take the bus, walk, ride a bike, etc. So a census, I could ask every student by doing a survey, but in any kind of data collection, in your sampling technique, you're going to leave people out. So that's why some people do a convenience sample. A convenience sample is exactly what it says it is. I'm going to ask people that are close to me. I'm going to publish this survey on Facebook and ask people a question. It's still a survey, but the way I'm sampling is called a convenience sample. I'm going to stand in front of the grocery store and ask people questions about who are you going to vote for? So that's a convenient sample. It's easy to collect the data, and the data still is useful, but it's not as good as other data collection sampling techniques. Next sampling technique is called a systematic sample. So if I'll use some kind of system to collect the data. I know that police departments say that they do this when they have the DUI checkpoints and things like that. We're going to pull over every fifth car and ask them for the driver's license, check their car, things like that. We know that sometimes they target different cars. I know I had a car in my 20s that was lowered and I had rims on it and everything. It was so cool. I went through the checkpoint and then I got pulled over. They asked me for my driver's license. What was I doing? Where was I going? And then they let me go. So systematic sample, you use some kind of system every fifth car. If I'm using my seating chart, I'm going to ask every fourth student, can you participate in my survey? That's a system. Another group of questionnaires would be that are not those are simple random sample, often called an SRS for simple random sample. It's kind of unique because a simple random sample and a stratified random sample both have the letters SRS, but whenever you see SRS, that's implied simple random sample. Later on, I'm going to show you how to collect data that's a simple random sample using a random digits table. That's kind of broken down on page 21. I'm also going to show you how to use technology. And there's a couple of problems that say use technology. That's using your calculator to come up with random numbers. Stratified random sample means you're going to break into groups. You're going to do a simple random sample, but you're going to break into groups first. So we're going to do groups. And then after we break you into groups, I'm going to put a G. After we break you into groups, then randomize. So that's a stratified random sample. Break you into strata, which means groups, and then we're going to randomly pick people. So a stratified random sample is a form of a simple random sample. It's just a little bit better. So an example of this, if I'm going to collect data from a high school group of students, I could ask 100 people in the high school, who are you going to vote for homecoming queen? And I get a pretty good sample representative of the population. I get a statistic, 60% are going to vote for candidate A. That's nice. It's a simple random sample. It's reflective of the population. But a better way to collect data would be to break everyone into groups first and then take a number of each group. Break you into strata. So this is pretty easily done. There's 9th, 10th, 11th, and 12th graders. There's your groups. Then I'm going to collect, say, 30 people from each group. 4 groups of 30, that's 120. I have stratified random sample. So I break you into 4 groups, then collect 30 from each group. And I'm going to find the average or the percent of people that are voting for the homecoming queen for each of those groups. So that's breaking you into strata and then collecting random data. A cluster sample is very similar to a stratified random sample. A cluster sample is breaking into groups and then collecting everyone from that group. So the book actually distinguishes between these two things. If you go to page 22 in your textbook, again, if you're using the 6th edition, it might be a different page. When I first saw this picture about stratified random sampling, I first thought these were milk cartons for some reason, but they're actually like pictures of homes. So I have 3 groups. I have low income, middle income, and high income groups. Then I'm going to randomly pick some people from each of those groups. So break you into groups, randomly pick from each group. Okay, a cluster sample down below, zip code zones by region. So I got 4 zones. I'm going to break you up into zone 1, 2, 3, and 4. And then I'm going to sample people in zone 1 and see if that zone is representative of the entire county. There's a picture of homes again on systematic sampling on page 23 that breaks people up by a system. So it looks like every third house is selected. They actually show how to use a table of random digits, which I'm going to get to. That's more for simple random samples. So again, if we're going to do a simple random sample, I'll show this a little bit later. We could use the table of random digits, or we're going to learn a little bit about the calculator today. You don't have to use the TI calculator, though I will use the TI-84. If you have the app on your phone, that's really useful. You could use Get More Math. You could use the calculator that's online. So there's several different calculators you can use. The app is probably the cheapest and most convenient for you. So I would recommend to do that. But I'll come back to those items. We'll do a new page about sampling using the table of random digits. There's a snippet of it on page 20 in the textbook, or I'm sorry, page 21. We'll come back to that. Actually, you know what? I take that back. Let's do it now because it doesn't make sense to come back to it. We're still talking sampling. I'll come back to experimental design. So what I'm going to do is I'm going to open a new page and let's talk about the table of random digits. So again, it's table 1, random numbers, integers. So the random digit table. So the table is on page and in the appendix. Appendix A. So I'll go to the back of the textbook. There's the appendix. There's answers are back there and stuff like that. Or I'm sorry, it's appendix B. Got that wrong. Appendix A is just extra information, like extensions and stuff like that. Appendix B is where all the tables start. We're going to learn how to use about 7 or 8 different tables. So somebody a long time ago invented a table of random digits. Each row is separated by a bunch of numbers. And within those numbers, I'm going to look at the numbers by every 2 digits, every 3 digits, or every 4 digits, or even single digits. So my best example is this, okay? There are 36 students in class. Let's randomly select 5 students. Okay, so I'm not picking on you if I call your name, but I randomly select you. We're just going to use the first row. It's broken down by rows. There's row 5, 10, 15, 20. It's just grouped different digits. So I'm going to use the first row. I'm going to go every 2 digits. So I'm going to write down these numbers. 92, 63, 07, 82, 40. You might have noticed something there. 92630 are the first 5 numbers. Then you go 78240. Well, the 0 and the 7 went together. Okay. The number, just because there's a break doesn't mean the numbers don't go together. 19, 26. I'm going to keep going because I need more numbers. 79, 54, 57, 53, 49, 72. Ooh, 38, so close. 38, 94, and 37. Hopefully you're following along where these numbers are at. Okay. etc., etc., etc. Let me spread them out this way so I can look at them better. All right, so I went every 2 digits. I want to select 5 people in a class of 36 students. So I'm going to assign you a number. If you're student number 1 on the list, on my H number list, student number 1 is 01. So I'm looking for 01, student number 1, but I'm going to go in order. Student number 92. We don't have 92 students in our class. Student number 63. There's not 63 students in our class. Student number 7 is my first random student. So I could easily go to the student list and look up student number 7 on my student list. And Danielle. Danielle, student number 7 on my student list. First random student selected. Student number 82, student number 40. I'm skipping these numbers because those numbers are greater than 36. Student number 19, 26. And I think all of these numbers are above 36. So I did not actually select 5 because the numbers keep going, but I selected student number 7, student number 19, and student number 26. Those are my first 3. Obviously, I would keep going to get my 3rd student, or my 4th student and my 5th student. So that's random selection using the table of random digits. We don't always go by 2 digits. Okay, and there's an example of this. Let's say I have a company like SpaceX here at Vandenberg. We have SpaceX in general, there's thousands of employees, right, in California. So out here, I want to pick, let's say, 350 employees, and they're all going to get random. I'm going to randomly give them money because I got a lot of money, and I'm the CEO and owner of SpaceX. 350 employees. I'm going to give everybody a $50 gift card, random. Okay. Now I'm going to select those 350 employees out of thousands of people. Now I'm going to go every 3 digits. I'm going to use a different line. So I'm going to go to, let's just do line 10. So I got person in my company, person number 421, person number 030, person number 278, person number 173. Hopefully you can find those numbers. So just like previous, I have person in my company. I have 350 employees that I'm selecting from. There's not 421 employees, so I skipped that number. Person number 30 wins a gift card. Person number 278 wins a gift card. Person 173 wins a gift card. So it's random. I randomly selected people, so nobody could say that wasn't fair. I used a table of random digits, and you could Google this. You could Google a table of random digits. You'll get different random digit tables. You could actually Google this textbook and get this exact table on your computer if you don't want to use your textbook. So that is a random digits table. There are other methods of randomly selecting data, and this is called using technology. So hopefully you got a TI calculator. 83 works, 84 works, 81 and 89. And there's a TI Inspire. Those are a little more funky with the way they do things. But the 83 and 84 are a little more aligned. Excuse me. So they work together pretty well. The TI 84 has what I refer to on is the calculator that I use all the time. The TI 84 has a lot of technology that we're going to use in statistics. You may have seen it already, so let's take a look at the calculator. There's a button that says stat. We're going to use the stat button a ton in this course. When we press the stat button, we're going to go to stat calculate. We're going to go to stat test, stat edit. We're not going to use that button right now. We're going to use the math button. Amazingly, there's a button that says math. Third button down on the left side. If you're using an app, graphing calculator app, hopefully you got to the app. The math button is on there as well. We go to math. Then after we go to math, we're going to go PRB. PRB actually stands for probability, although this is not a probability. And finally, we're going to go to rand int. Here's my calculator. Rand int is number 5. Might as well put that on there. Number 5, rand int should be about the same. Calculator might operate a little bit differently. We have 2 or 3 choices that we can do. We can do a lower bound and an upper bound. Okay, so this is the first time we're using the calculator. It's okay. You learned how to use a cell phone without any directions, I'm sure. You didn't go through and search online how to use my smartphone. So the calculator, no different. You're not going to break it. But calculator has that wizard. Let me go like this. Try to get on it. Okay, so there's 2 different ways to use random integer. The LB means lower bound, so it asks for a lower number. The UB means upper bound, asks for the biggest number. When we hit this button, rand int, we're going to enter the lower bound and upper bound. The number of trials is in a bracket. We don't have to enter the number of trials. So we use the first rand int, LB, UB, and number of trials, we put 1, or we don't put anything at all. It's going to say rand int 1, 36. Let's do rand int. So I'm just going to use the first one, like the problem that we just did. We're going to pick randomly 36 people in this course. 1, 36. Press enter. I got random number 29. That's a random number. Let's enter again. I got random number 35. Our calculator uses an algorithm to randomly pick numbers. Pretty cool. That's rand int on the calculator using statistical software. Okay, the problem, I think in chapter 1.3, I think I removed the problem, or there's 2 problems where you have to use statistical software to calculate or collect random integers. So this is problem 20, 21, and 22 on page 25. It says to list the number of 37. So you got 37 people. You're going to randomly select 4 patients, it looks like. So you want to use the random digits table, and you can use, or the random function on the calculator, rand int. Problem number 22 says numbers are 1 through 90. There's 90 volunteers. Okay. Or I could use, for the second example, 350 employees, I could do rand int, and I could do 1, 350. And let's say I want to select 5 employees. What this will do will give me 5 random numbers. Okay, so 5 is the number of integers you're going to select, or it's called trials. So when I do that, rand int 350, 5, I'm going to select 5 random numbers between 1 and 350. First number, 78. Second number, 130. 328. Finally, 38. Random numbers. There we go. I got 5 random numbers between 1 and 350. And one property about simple random samples is that each, if you're selecting people, you usually call them subjects, Each number is equally likely to be chosen. Every person has an equal chance of being chosen. Okay, a stratified random sample, you kind of eliminate that. For example, at SpaceX, let's say there's 50 females and 300 males at SpaceX. 50 females, 350 or 300 males. I want to stratify by gender, and I'm going to pick out of 300, I'm going to pick 5 males and 5 females just to break it up into groups, then randomly pick from each group, stratified random sample. All right. Lastly, but this is secondly in the book, you might have noticed that I kind of went out of order a little bit. That's okay. We're still talking about the same stuff. Now I'm going to talk about properties of experiments. So experiments have several different properties that we can have. There was the Coke Pepsi challenge back in the 80s, and the Coke and Pepsi, they had the commercials. And what do you like better, Coke or Pepsi? There were confounding variables in this study because people that liked Coke often already had a liking of Coke. People that like Pepsi, they already drank Pepsi, but they always battled against each other. And there was all these commercials about the Coke Pepsi challenge. So that was kind of a big deal in the 80s. I know I don't look that old or act that old, but I still remember those commercials. Anyways, that's sort of an experiment. If you want to open a coffee shop, you think your coffee is better than Starbucks, go for it. I commend you on doing that. Everybody loves Starbucks. The line is around the block waiting for coffee at Starbucks. But if you want to do a true taste test, then you can do an experiment, okay, and decide which coffee is better. Maybe do this at a college and see who could pick the correct coffee. So in an experiment, one of the things that we would like to do is set up a completely randomized design. Completely randomized means there's going to be a treatment group and control group. Well, in the Coke Pepsi challenge, there's not necessarily a control group. Okay, you have 2 treatments imposed, but in a completely randomized design, we're going to take 2 groups of individuals and put them into 2 different groups. So if I have a treatment group and control group, what I'm going to do is take, let's say if I take 100 people, I'm going to do a study on a new drug, and I'm going to call it the smart pill. Okay, I want to know if the smart pill makes you smarter. This is a good one. I should have invented it. I'm going to put 50 people in the treatment group, and I'm going to give them the smart pill and give them a pre-test and post-test and decide, does the smart pill make them smarter after 6 weeks, say. Then I'm going to have a control group. I'm not going to do much with the control group besides tell them that they're entered into a statistical study. At the end of the study, I'm going to look at the results. So here's my results. At the end of the study, what I just created there is a statistical design. So I got 50 in the treatment group, 50 in the control group. And one of the things I want to do is I want to randomize. I don't want, it doesn't have to be 50 and 50 either, but I want to randomly pick 100 people to be in my group. That usually doesn't happen, especially if you're doing a study on something that's significant like cancer research or other things like blood pressure medication, things that are really important in life. We would want to have a treatment group and probably not a control group, but another group called a placebo group. So in a placebo group, if I'm doing a smart pill study like I just kind of made up there, I'm going to have a placebo pill. What happens is if I say, hey, here's a smart pill, I want you to take this, you automatically are going to do things to make you smarter. You're going to study more. You're going to get better sleep. You're going to eat better because you want to get smarter. So I want to give people a placebo, a sugar pill, to eliminate the placebo effect. People think they're going to get smarter, therefore they will, by doing things that will make them smarter. okay, and help them do better on a test. So if I have a placebo group, that kind of eliminates confounding variables and helps me with my experiments. Okay, again, I mentioned experiments. Usually you're going to randomly select, and we want to randomly assign people into different groups. That's called randomization. So if I randomize, I eliminate chance variation, or I create chance variation, which eliminates confounding variables. Okay. Another element of a well-designed experiment is called replication. If replication has two meanings, I could replicate the study. So if I do an experiment, I would like to do the study or the experiment one more time, replicate that experiment to make sure I don't have any confounding variables. Make sure if I'm giving, especially medication, medication is very important. If you're doing a study on COVID-19 and you're giving people a shot, a vaccine to make sure they can't get COVID-19, then you better be sure about your findings, right? I use that example loosely. I don't have any opinion for or against vaccines, but there is a movie out there. It's called The Vaccine War. I highly recommend it. It was filmed in the 90s, I believe, and it's just about vaccines and their use over the last 40 to 50 years. Okay, polio and do vaccines cause autism, stuff like that. So this was way before COVID was really known about. Anyways, that's replication. Control, that just means you need a control and treatment group if you're going to do a study. If you do an experiment and you don't have anything to compare it to, for example, if I'm doing a cholesterol medicine, the most prescribed pill in the United States, Lipitor, is cholesterol medicine. We want to lower cholesterol to eliminate heart disease and heart attack and cause of death. So cholesterol medicine, I don't want to just give 50 people cholesterol medicine and be like, oh, it lowered your cholesterol. I don't have anything to compare it to. I need a control group. I need a placebo group. So that way I have things to compare to. That's control. So those are three elements of a well-designed experiment that are very useful in helping me have good results. Another word up there, properties of experiments, blocking. So within blocking, I'm going to create blocks, and you can block by, most common use of blocking is blocking by age. So I could put you into blocks, especially if I'm doing a heart disease study. So I'm going to block by, 40 to 50-year-olds, 50 to 60-year-olds, 60 to 70-year-olds. We'll talk about interval level of measurement and creating those intervals later on in chapter 2. But for right now, I'm just talking about blocks. You can block by gender. Males and females react differently to different medications, to different drugs. So we want to block by gender, and I'm going to look at the results of males and how they were reacted to these certain medications. That's blocking. A matched pairs experiment is a form of blocking. I'm going to take two people. Let's say I'm going to take two females that both weigh 120 pounds and are about the same height. They have the same ethnicity. I'm going to put them into two different groups. I'm going to put one in the treatment group, one in the control group. And at the end of the study, I'm going to compare those two people. Then I'm going to do two females that are 130 pounds, same ethnicity, put them in two different groups, compare them at the end. So my results, if they're significant, I know that there's a difference in matched pairs. You pair up by similarities and look at the results at the end. I already mentioned the placebo effect. Sometimes if you get treatments, the placebo effect, people get better. And it's not because of the medicine that you give them, they get better because of other things. And a good example of this, the placebo effect, if I got a new diet, right? There's thousands of diets. I have a saying, people spend the first 30 years of their life trying to gain weight and the rest of their life trying to lose it. So diet and exercise are all really important. I put people on a diet and I want to know if this diet works. I'm going to do the vegan diet. Did people lose weight? Well, within people taking or doing the vegan diet, some of them exercise. So that's a confounding variable. that confounding variable will affect my results. So I want to avoid that situation, the placebo effect. You think you're going to lose weight, therefore you will. You're going to do other things to help you lose weight, like exercise on the side. Besides eating healthier, you're probably going to drink more water, probably going to get more rest. All those things are factors into doing better. I just realized right there I spelled double blind wrong. Forgive me. I'm not a English major. I'm a math major. So blinding and double blind. If you are going to do an experiment where you have blinding, that just means myself as an experimenter, I don't want you to know if you're in the treatment group or control group or placebo group. You, as entering the study, are blind to what group you're in. If you're in a placebo group, you think you're getting the medicine, you think you're in a clinical trial, and in this clinical trial, you're getting a medicine and you think you're getting better, although they're giving you a placebo, okay, a weight loss pill. So they could give a placebo group and a treatment group. Usually, with things like that, if it's affecting your health or affecting your livelihood, usually those sample sizes will be really small. And when you have small sample sizes, replication and confounding variables are a factor. Therefore, we can't really apply the results to the entire population. Double blind means that you're going to be blind as a person in the study, and also the experimenter is going to be blind. So you have like a third party, we call it the middleman, is going to put people in the groups. They're going to give the researcher all the results. The researcher has no idea who's in what study. They only look at the data. And Dr. Fauci talked about data all the time. Love him or hate him, but he talked about data. We got to look at the data. What's the data say? And decide what's best for the population. And that's chapter 1 in a nutshell. Hopefully you learned a little bit about chapter 1. Please keep up with the homework. Please do your best to work on the quizzes and the test and stay on top of this course. All right. Have a great one. Bye.